Hello everyone, welcome to the lecture. So before we start the topic of today, which is combining design stage and random uncertainty, I would like to talk about the accelerometer that we have. So we have the accelerometer CXL04 GP3, right? This is a 3-axis accelerometer, and it has an input range of plus minus 4G, okay, and it also has the sensitivity, right, of 500 plus minus 15 millivolts per G, okay, and when you look at the spec sheet, we have found a number of things that are related to instrument error, and there's one item that was related to zero order uncertainty. To sort of refresh your memory, we have design stage uncertainty, which is called at UD, right? Is a combination of U0 square plus UC square, right? In square root. And this is related to your resolution, and that's related to your instrument error. Okay, so we went through all the lists that we have in that spec sheet, and we'll do that in the laboratory with you. So if you didn't do this part, don't worry about it. We'll just do it together. Okay, I'm going to move the screen a little bit down because you're not able to see the top. Okay, and then now the goal here is to figure out what is the resolution. Okay. So one particular item that you have found in the spec sheet is related to noise, okay, and the noise was given as 10 microGs, okay, times voltage RMS, okay. So in that case, we are going to use that information to calculate our resolution. The other thing that we had that's important was bandwidth, okay, and that was given as DC 100. In other words, this was spec'd up to 100 Hertz. Okay, why this is important? Okay, because the resolution of a accelerometer, okay, is given as, okay, the noise times in square root bandwidth, okay, times 1.6. Okay, so since we know the noise is 10 microGs, correct, and that is equal to 0.01 Gs, okay, and in basically spec sheet, right, in calculating the resolution in conjunction with the instrument error, there's two rules that we have to follow, right? Number one, everything has to be in the same units. And number two was that we're going to use RSS to combine. Okay, so to make everything in same units, I'm going to use in this example or throughout this accelerometer sort of work, I'm going to use voltage. Okay, you can use G's as well. That's up to you. It works the same way both. But the general rule of thumb is to use the output that you are reading from your sort of sensor, and in this case you are reading voltage output, right, from your accelerometer. Okay, so in that case, if I were to convert this G into voltages, right, I know my sensitivity here, right, it was given as 500 millivolts per G, right. In other words, it is the 0.5 volts per G, right. And if I were to convert that, then I will find it as times 0.5 volts per G, right? G's are going to cancel each other out, and I am going to find 0.05 voltage as the noise of the system. Okay? Now we know the noise, right? At least as in voltages. I'm looking back to my noise again, right? It was given as here as the 10 microg's times the voltage in RMS. Okay, so I know that the input range, right, as plus minus 4 G's, right, that was written on this here on the top. Okay, so therefore the worst case scenario, right, it's a little bit clean, input range was plus minus 4 G's, okay, and then the worst case scenario is what we want to do in our design states uncertainty, right? So that means that if we are measuring it RMS, I could take my maximum acceleration that I will get as 4G. Okay, and looking at this, the noise is given as the microg's times the acceleration in voltages. So if I were to convert this, right, I will find that this is related to times 0.5 volts per G. Okay, G's are going to go away, and that's basically 2 volts. Okay, so in that sense now we can go ahead and figure out what the noise of the system was, right? Is 0.05 volts, right, which is sort of the base noise, and at 2 volts, which is also at 4G, right, it's the same thing, they're just converted to each other, right, then it will going to get me, this is going to get me 0.1 volts, which is my noise. Now, looking back to my resolution, right, formula, it says that it's going to be my noise times my bandwidth, which I know to be 100 Hertz, because it was DC 100 times a constant 1.6. Therefore, my resolution will be calculated as, okay, 0.1 volts, which I've calculated from here, times in square root 100, okay, times 1.6, and this will be 0.016 volts, and that's going to correspond to 160 millivolts. Therefore, my U0 then, right, is defined as half of my resolution, so that will be plus minus, okay, 1/2 times 160 millivolts, and that's going to be plus minus 80 millivolts at 95 percentile. Since it was not given, I can assume that was my resolution. So, knowing this, your homework now right, is figure out what the design states uncertainty was, right, which is again a combination of U0 square plus UC square. Since we figured out what the U0 square was, now your job in the homework is to figure out what is the instrument error. Again, you got to do two things. One, same units. You have to compare and bring back everything to same units. Okay. And number 2, you're going to use RSS to combine them. Okay, now we have armed with the information that we have for the homework. Now go back to our lecture, which is combining random and systematic errors. Okay. So let's do by example, because examples are sort of easy to follow and also gives us a framework by which you can work our sort of concepts, okay? Let's say I am trying to read 2 things, pressure and temperature, okay? So let's do a reading, okay, from 2 different sensors, okay? I do pressure, which I'm gonna call P, okay? And the units are PSFA, okay, which is also given as the pound feet squared. And my temperature, all right, is given as T, and this is given in Rankine scale, okay. When I look at my spec sheet first, okay, to figure out what my design stage uncertainty is, right? When I look at the P instrument error, right, is plus minus, okay, 1% of the reading, whatever that actual reading of pressure is. And that's at 95 percentile. My T instrument is plus minus 0.6, okay, Rankine. That's at 95 percentile. Okay. The other thing, right, so these are the spec sheets, so we are assuming that the U0 is 0, and UC are these values, okay? Just for simplicity, because they are not really in here just to calculate, you know, those type of things. Okay, so then I also take a bunch of different measurements, okay? For pressure, which I've taken 20 samples, okay? Which makes my degrees of freedom 19, okay? Read a mean pressure value at 2,253.91 PSFA. Okay, that's what the mean value. Okay, and my standard deviation out of those 20 measurements was for the pressure is going to be 167.21 PSFA. I have done the same thing for temperature, okay. I have this time, however, instead of 20, I've taken 10 samples, okay. My average was 560.4 Rankines, okay. And my standard deviation, right, of temperature was 3.0 Rankines. Okay, good. Again, degrees of freedom for temperature is since n-1, and that's going to be 9. Okay, so the question is, using these 2 terms, okay, pressure and temperature, I'm calculating a gas density, okay, and then the gas density rho is defined as pressure divided by a R times T, okay. And in here, R is the Rayleigh gas constant, which is given as 54.7 feet pound force divided by LBR, which is temperature, Rankine. Okay? And the temperature. Okay? So the question is that we are trying to deal here is that what is, okay, the confidence interval, okay, of the gas density, so basically the true value of gas density, we think, based on the raw measurement that we have, based on pressure and temperature, plus minus U raw bar at 95 percentile. Okay, so we know what this is based on the measurements because we measured the P bar and T bar, and then we know the equation here. However, we don't know what is the uncertainty of here. So to do that, we are going to have to combine, okay, both random error, okay, which is defined as S rho bar, okay, and the systemic error, which is defined as B rho bar, okay. And S rho bar and B rho bar are the combination of, okay, SP bar and ST bar, and this is the combination of B P bar and B T bar. Okay, so we are going to first find these items, and then we are going to figure out how we're going to combine these two to find the U rho bar, which is the combination of both random and the systematic errors. Okay. Okay, here's something that we're going to have to figure out. I will give this as a rule, okay, and that's an important rule, that when you are combining random, okay, and systematic errors, right, so when you're combining SX bar, okay, with a BX bar in general, okay, you do it at 68 percentile. Okay, so that means, so what that really means, right? So remember, when we are looking at a distribution, a normal distributed setup, right? Let's say this is our X bar, which is the sample mean, okay? And then we are measuring our standard deviation, correct? And the standard deviation is X bar plus, right, sigma, and this is X bar minus sigma, okay? And this region, okay, is corresponding to 68 percentile, right? So in other words, 68% of the population is expected to lie within the mean and the first standard deviation, okay? You can do the same thing for the 95 percentile, but at the 95 percentile, let's say this is my 2 alpha, and this is my 2 alpha, okay? This becomes 95 percentile. In other words, we expect 95% of the population to be within 2 standard deviation away from the mean. Similarly, if you do this for, let me use a different color, 3 alpha, when I'm calling alpha, I mean sigma, I'm so sorry. This is then 99 percentile, meaning that we expect 99% of the population to be around 3 standard deviation away from the mean. Okay, so with that definitions in mind, 68 percentile represents, okay, the uncertainties before a t-score adjustment. Okay, so what that means, so if you remember that that we compare, or we found the standard deviation, right, of a system. So remember how we calculate the random error of a system, okay? So we do a t-score at certain degrees of freedom at certain p-value times, right, its standard error, Sx bar, okay? So Sx bar, as calculated, is always at 68th percentile, right? Again, Sx bar is directly proportional to your standard deviation, and therefore it is at 68th percentile. If you look at the t-value of a large sample size, say infinite, 95, this is your table 4.4, by the way. You should have access to it in your lab, so in your class notes, is approximately 2. So therefore, to get the error at 95 percentile, we multiply 2 times, okay, Sx bar, which is at 95 percentile, okay, that gives us the error at 95 percentile, right? Because we adjusted with the t-value, right, and then multiply by 2 to represent the 95% of the population. Therefore, when you calculate your standard error, okay, or standard deviation based on the random error, you can assume that that's at 68 percentile. So what happens with the systemic error? Let's say you go to a spec sheet, okay, and read the error at 95 percentile, right? So let's say they gave you a bx bar, okay, at 95 percentile. The standard deviation or standard instrument error at 68 percentile is simply you are dividing it to the t adjustment value that you multiplied it in the beginning. So in other words, the bx bar at 68 percentile is equal to, okay, bx bar, which is given at 95 percentile, divided by the t value, right, of that degrees of freedom and 95 percentile. In spec sheets, we can always assume that this is infinite because it's a large sample size, and at 95 percentile is what you use. You can assume that's around 2. So that means that bx bar is equal to the 95 percentile systemic error divided by 2. Okay, so basically the rule here is that you always want to convert everything to 68th percentile to combine. Of course, you have an option to convert everything to 95 percentile combine, but 68th percentile makes it easier because your standard deviation, right, always given at 68th percentile by definition, right? So then you just compare your calculate your random uncertainty and convert your systemic error to 68th percentile, because no guarantees that the systemic error can be given at 95. It could be given at 68 or at 99. So you just want to make sure that everything is at 68th percentile before you start doing anything with it. Okay, so then now we have armed with that knowledge. Let's try to figure out what is the gas density uncertainty and combine the systemic and its random errors together. Okay, so the pressure systemic error, okay, systemic error, okay, was given as, from my spec sheet, okay, as the 1% of my pressure reading. Okay, so at 95 percentile. So now I know that the the systemic error at 68 percentile, right, which I'm going to call this big B, right? The small b for pressure is going to be 1 over like half of what 95 percentile pressure was, right? And therefore, it's going to be 1 over 2 times, okay, 0.01, that's my 1%, of the real reading that we got, right, which was given as 2253.91. Okay, so that's my P bar reading, okay, and that's going to give me 11.28 PSFA at 68 percentile because I divided by 2. If I didn't do that, I would have calculated at 95 percentile. Okay? So, let's go back to the random error, pressure random error. Okay? So, I was given my SP as 167.21, okay, and my sample size was 20. The only thing that I need to calculate here, and you can imagine that my standard deviation was already in 68 percentile because standard deviations always are at 68 percentile. Let's write the units, don't miss the units. Is PSFA at 68 percentile. Okay, so all I need to do is to calculate my standard error, which is defined as SP divided by square root of n, and that's going to get me 167 times 21 divided by square root of 20, and that's going to get me 37.39. Let's don't forget my plus minus here. Plus minus 37.39 PSFA at 68 percentile. Okay, pretty easy. Okay, so what happens to my temperature systemic error then? Temperature systemic, okay. My systemic error at 68 percentile, which I'm going to say small bt, is going to be 1 over half of big BT, okay, and that's going to be 0.6 Rankine divided by 2, okay, and that's going to be plus minus, okay, 0.3 Rankines at 68 percentile. Okay, and my temperature random, right, is going to be basically my standard error, right? That's going to be ST bar is going to be ST divided by square root of 10, okay, because my n was 10 in this measurement, right? And then it will be 3 divided by square root of 10, and that's going to be 0.9 Rankines plus minus at 68 percentile. Okay, there you go. Now I have all my different errors, right? Now from that, I need to calculate, okay, my B rho bar, which is the systemic, and my S rho bar, right, which is random. Okay, and these are coming from, right, B P bar and B T bar, and this is coming from S P bar and S T bar. Okay, so therefore we have to use the error propagation that we have done in the last class, right? So therefore, rho is a function of pressure and temperature readings, okay? Therefore, the error B rho bar, okay, I'm going to use my sort of the partial differential rule, partial differentials, right? It's going to be d rho over dp times bp bar, okay, this is in squared, plus b rho over dt times bt bar squared in square root, okay. D rho over dp is going to be 1 over RT BP bar, right? Squared plus minus P over RT squared times BT bar. Okay, so that's that. Squared square root. Okay. If I put all the numbers in, okay, I will find that my error, systemic error for the gas row, right, is going to be plus minus 3.7 10 to the minus 4, okay, lbm or feet cubed at 68 percentile. Okay, I can do the same thing for my S rho bar, right, which is again defined as d rho over dp times sp bar squared plus d rho over dt times st bar square and square root. Okay, if I do this, what I will find is that it will be plus minus 0.0012 lbm over feet cubed at 68 percentile. There you go. So now we both got S rho bar, okay, and so B rho bar and S rho bar, as well as the rho bar, right, which was the given as 2253.91, which was P bar divided by RT, right? And then the RT was, let me write just the numbers so we can get over with. The R was 54.7 times the temperature, which was 560.4. So this was the Reynolds number, and this was the temperature bar, and that gives us 0.0735 lbm feet cubed. Okay, so we have the systemic error, we have the random error. They both are at 68 percentile, which is great. And I have my average rho bar. Okay, all I need to do now is to combine the B and S to reach to U rho bar. Okay, how do we combine the two? Now we got both of them at 68 percentile. Okay, so to do that, we need one more step, because the U rho bar is defined as, right, since we wanted it 95 percentile, we're going to have to do the T adjustment, okay? U rho bar is defined as, right, T degrees of freedom at 95 percentile times U rho bar, and U rho bar can be defined as just like RSS, right? That will be then B rho bar square plus the S rho bar square in square root. So the question here is that we are trying to figure out is what is the degrees of freedom. Okay, degrees of freedom for pressure was 20, and degrees of freedom for temperature was 10. So how do we combine the two to get a sort of a combined degrees of freedom? While it is lengthy, we have a good let me fix that right there. These were not 20 and 10. This was 19 and 9. Good that I catch that. So to combine this, we have a lengthy formula, but it's pretty simple. V rho, which is degrees of freedom. Okay, I'm going to make a big divider here. Okay, is going to be this. D rho dp times sp bar, okay, plus d rho dp times bp bar, okay, squared, both terms, okay, plus d rho over dt times st bar squared plus d rho over dt times bt bar squared, and all of them also squared. At the bottom, what we have is again d rho, let me write it a little bit better. So we have d rho over dp times sp bar, okay, that's 4th power, divided by vp, degrees of freedom, plus d rho over dt times st bar 4th power divided by degrees of freedom of t. Okay, and then we do the same thing for the other term, which is d rho over dp times bp bar divided by vp spec sheet. I'm going to get to that. 4th power plus d rho over dt times bt bar 4th power. Okay, and that's divided by degrees of freedom TB. Okay, so we know that these degrees of freedom here, that I'm going to circle with red, are the degrees of freedom that we measured from random error. Okay, and these are the degrees of freedom that we take from spec sheet. So we don't know what's the numbers that engineers used in the spec sheet, but let's say we are going to have to assume they are larger than 100. So therefore this term goes to 0 because we actually don't know these numbers and we are just basically doing that. So if you do this math with that term cancelled, we'll find that, oh, yikes, what was that? Let's go back, lead, and let's go to black color. Okay, there we go. If you do this math, you'll find that your new degrees of freedom is going to be 23. So comparing this to pressure and temperature degrees of freedom, you see that it was 19 and 9, and the combination adds to 23. So it's not as good as combining them together, right, to reach a like a larger number like 28, but still increases your statistical power and carries it out to 23. Therefore, now we have everything we need to combine the two, okay, U row bar is then T23, right? That's the degrees of freedom we just calculated for row, okay? 95, okay, times B row, right, squared plus S row squared in square root, okay? And let's use this number from our table 4.4, okay? And that will give us 2.06. Okay, so then U row is going to be 2.06 times, okay, 0.00126, which is this term if you're calculating it, okay? So therefore, U row is going to be plus minus, okay, 0.026 lbm feet cube at 95 percentile. Okay, therefore, we can say that the confidence interval, meaning that based on the measurements that we have, we think that the real value of the row, right, it lies between the measured value 0.0735 plus minus 0.0026 lbm feet cube at 95% confidence. There you go. So we were able to combine the systemic error with the random error and come up with a overall error estimation for our reading based on this.